So hello everyone. I am Younes, a PhD student in Advanced System Engineering Laboratory at National School of Applied Sciences in Ibn Tufayl University. And the work that I'm going to present is the modelization and a design of longitudinal and lateral control system for a four-wheeled robot with feed-forward controller. And this work progressed through a sequence of physics-based increasing fidelity models that are used to design and develop the robot controller, respecting the limits of the robot's capabilities, and develop both a simple geometric control and a dynamic model predictive control approach. So I worked mainly on the following challenges. First is to have a model that unified two systems in a streamlined way and combine their notions together. The first system is the adaptive cruise control with its ability to maintain the object speed at a predetermined point and keeps its speed constant, controlling the fuel injection in the engine or the intensity of the electric current in the motor, as in our case. The second system is the lane keeping assistant that automatically corrects the steering to bring the object back into its main trajectory. Second, most actuators have significant torque variation that cause focal disturbance effects at speed below 13 meters per second. Neither ACC or LKA systems actuate properly at speeds lower than that. It's therefore challenging to develop a controller using only PID for both systems that works well at speed below 13 meters per second. And for that, we came to the third challenge using one feed-forward controller to reduce nonlinear nature of the robot dynamic and kinematics in both longitudinal and lateral movement, especially for target low speed range of 1 to 13 meters per second. So in this presentation, we will go through a development for the kinematic model that represent the four-wheeled robots based on the unicycle and bicycle model, and how these models will aim to capture the dynamic system reactions to input commands such as steering and velocity, and how it reacts to disturbances. The kinematic and dynamic model that we will define outline the effects that input and disturbances have on the state of the robot, such as the velocity and the rotation rate. Therefore, the controller's job is to regulate some of the robot state by sensing the current state variable and generating actuator signal that satisfy the commands provided. For example, for longitudinal control, the controller sensing the robot speed and adjusts its command match to match the desired speed set by the autonomous motion planning system. And for that, we call that cruise control. For lateral control, it must select the steering angle required to correct the track changes and any errors that accumulate in the path directions in the moment that they appear, and it named lane keeping. So generally, robot's motion can be modeled either by considering the geometric constraint that define the motion of the robots, and it's known as kinematic modeling, or by considering all the forces and moments acting on it, known as the dynamic modeling. In our case, and as much as we are working in a low speed range, the accelerations are not very significant. So kinematic modeling is more than sufficient to capture the motion of our robots. The figure represents the kinematic model for the robots used for this study, with A, the midpoint of the wheel axis, R represent the diameter of the wheel, 2L represent the robot width, Phi-R, Phi-L represent the rotation rates, velocities of the right and left wheels, and finally, theta is the angle of orientation of the robot. Before we start modeling the robot motion, it's important to take into consideration as a first step the coordinates frame for this representation. We take for our 2D transformation the global world frame XF, YF as a fixed coordinate system, and the body frame XY as the mobile frame linked to the robot. We named points of the fixed coordinate system QF that's characterized with abscisses, ordinates, and the orientation of the robot, and Q, same thing as a landmark for the mobile frame And in the concept of the coordinate frame transformations, R theta is the orthogonal matrix that relates QF and Q. So now, in order to make the kinematic control study for this robot easier, we separate this modelization into two more simple different forms that depends on the nature of the robot's movements. For longitudinal movements, we treat it like a unicycle robot, assuming that there is neither lateral nor rolling slip. And for lateral movement, we treat the robot's kinematics like those of a bicycle, assuming that only the front wheel can be steered and that both the front and the rear wheels are combined into unique wheels at the center of the front rear axles. And we are now ready to start kinematics for our unicycle robot. The robot's motion is constrained to move only forward and to ensure the longitudinal movement for the robot. And because of this constraint that wheels points in only one direction, it's called a non-holonomic constraint, which means that it restricts the rate of change of the robot's position, so the robot can roll forward or backward and turn while running, but cannot move sideways directly, which means without wheel slipping. And based on that, we place two hypotheses for the right kinematic in our case. First one, no lateral slip means that the robot can move forward and backward, but not laterally. Second, no rolling slip, and that to assure that no wheel can slip to change direction at the expense of the other. So each wheel shall maintain 1 point in contact with the ground. Hypothesis one, suppose that like the representation of the robot in the video below, that can't slip laterally, the velocity of the robot associated with the point A is 0 along the lateral axis in the moving coordinate system. So we can derive the expression of the non-holonomic constraint equation as follows. Hypothesis 2 represents the fact that each wheel maintain a point in contact with the ground, which gives a linear velocity of each wheel of the robot at the point of contact P. So we can easily find the generalized equation of the two-wheel system based on the expression of the generalized velocities. And to summarize, hypothesis 1 and 2 produce the following constraints in addition to the linear velocities of the right and left wheels at the point of contact. The velocity of the robot can be computed as the average velocity of both wheels as seen from this figure. As much as the velocities of both wheels are the same, the robot moves in a straight line if we use the notion of the instantaneous center of rotation to define the kinematic model for our robots. We again have the rotational rate omega in terms of VL and VR. Combining these equations with our expression for velocities yields the final form of equation for the rotational rate of the robot in terms of the wheel rotation speed. Finally, we can write the non-holonomic constraint of the matrix EQ and the derivative of the generalized coordinates Q characterized by longitudinal and lateral velocities coordinate axes, rotational and both wheels velocities. So if we get back to our full-wheel robot, and this time we combine the front and the rear wheel axles into a unique wheels at the center, reducing them into a pair single wheels that are assumed to be side-free, and only the front wheels are steerable. We can develop the kinematic classic bicycle model that are used to be surprisingly well at capturing vehicle motion in normal conditions as a suitable control-oriented model for representing vehicles because its simplicity and adherence to non-holonomic constraints. We always assume that the robot operates on a 2D plane dominated by the overall coordinate of the rear wheel, XY. And to analyze the kinematic of the bicycle model, we select the reference point on the robot at the center of the front axle, XF, YF. Theta is the orientation of the robot in the overall framework, and delta is the steering angle in the body frame. We will use L as the length of the bicycle measured between the two wheels axles. As with the two-wheel robot, these are our main model states. And the velocity is denoted V and the point at the same direction as each wheel. This assumption refers to the no-slip condition, which requires that our wheel cannot move laterally or slip longitudinally either. Because of the no-slip condition, we can find the no holonomic constraint equation for this front and the rear wheel as follows. And again, because of the no-slip condition, we have from the similar triangle formed by L, R, V, and delta, the rotation rate of the bicycle omega is equal to the velocity of the instantaneous center of rotation radius R, and we see that the tan of delta is equal to the wheelbase L over the instantaneous turn radius R. By combining both equations, we can find the relation between the rotation rate of the robot omega and the steering angle delta. We can now form the complete kinematic bicycle model for the front axle reference point formed by the state X, Y, theta, and the steering angle delta. We can now use this model and the previous unicycle model to design the kinematic controller for the full control mode. So if we go inside this model, we are basically going to find the two models that we did study kinematically attached to the controller with an inverse kinematic model and its ratio. Promptly, the point of building an inverse kinematic model is to inverse and reduce the input from the operational velocities V and theta to the velocities of each wheel with their gear ratio to find the angular velocity of the robot's motors as a controller input. So now that we know all the components of the controller control modelization, we can go through each one of them and discover how to build a non-sophisticated model that can control both longitudinal and lateral movements in a low speed and reduce internal and external speed disturbances. Starting with the unicycle model that reduced the model into two-wheel robots concentrating on two rear wheels that actuate the robot forward. And so we need a kinematic modelization for the direct kinematic model to reduce disturbances and a kinematic model for the robot's posture to coordinate the robot position. For actuators, we are using DC motors known as converters of direct current electrical energy into mechanical energy that are used to drive the wheels of the robot passing by the equation of the electrical circuit with the counter electromotive force that can afford the rotational speed of the motor by applying Newton's law on the motor shaft. And with the torque produced by the engine, we can simply find the angular velocity of the robot wheels, as you can see in Simulink modelization below. Taking the voltage U used as the input of the motor, E is the armature current. The strength and inductance of the armature winding are respectively R and L. We consider VB as the electromotive force. Omega M and tau M are the angular velocity and the torque of the motor. The torque constant and the electromotive force constant are respectively K and Kp. G is the inertia of the engine, F is the damping coefficient, and finally N is the reduction ratio. So now after calculating the exact velocity of each wheel, we should return to the operational velocities using the direct kinematic model that allow us to know the Cartesian velocities and the rotational velocities of the tool coordinate system as a function of the position, angular velocity, and of the axis. And from the kinematic modeling, we can find the direct kinematic model equation and modelization. Velocity here is in terms of wheels rotation speed after regulation. And that's what makes it the perfect spot to do velocity, disturbance, and removal. And right after extracting disturbed velocity, we can place our feed-forward controller. The basic concept of feed-forward control is to measure important disturbances variables and take corrective action before they disturb the process in order to improve the performance results, especially when the robot starts at zero velocity. Feed-forward control has generally been considered as an advanced control method, and if we break it down into different stages, we obtain a comprehensive analysis of the planning and control system, a regular review of this system for input variables and interrelationships for the consolidated results, a collect data of input variables and synchronize this data with a developed system, frequently analyze a variation in actual input data and compare to the planned input and assess their effects on the expected result. And based on the analysis, take corrective actions to align planned and actual trajectories. So right after measuring these disturbances, anticipatory controller take actions for compensatory control. So basically, the controller adjusts the motor torque gain to increase or decrease the motor drive force FD in response to the command signal with the reference velocity and the speed sensor feedback signal. And we can find this equation of the longitudinal elements of the vehicle administered by the Newton's law. With M, dV over dt is the inertia force, Fa is the aerodynamic resistance, Fd is the driving force of the engine, and Fg is the force of descent. Planning the direct kinematic of this system starts with simplifying the model. Consideration is being given to setting all initial conditions to 0. A feed-forward control of the direct acting control system is illustrated in the simulation part, where the closed loop of GP, G0, and GFF yields the equations below. So right after finding the expression of GP and G0, we place the disturbance reducing gain of feed-forward GFF in our modelization. Now all parts are in its place to find the Cartesian parameters for this robot's position over time. And using the kinematic model of the robot posture, we can find the generalized coordinates of that are characterized by the longitudinal and lateral velocity coordinate axes, rotational and both wheels velocity and steering. To introduce feed-forward control, we skipped the modelization of the bicycle in order to use the undisturbed value of the speed to find the correct robot orientation and steering angle modelization. The controller chosen for this geometric trajectory tracking is pure tracking, and it's a controller it's a controller that only uses the geometry of the robot kinematics and the reference trajectory to follow it. And it's known as geometric path tracking controller. So the core idea of pure pursuit method is a reference point can be placed on a fixed distance ahead of the robot on the path, and the steering commands needed to intersect with this point using a constant steering angle that can be computed. As a robot turns toward the path to follow this curve, the point continues to move forward, reducing the steering angle and gently bringing the robot toward the path. In this method, the center of the rear wheel is used as a reference point on the robot. The target point is selected as a red point, and the disturbance between the rear axle and the target point is denoted LD, as you can see in the right figure. Our goal is to get the robot to the correct angle and then to get to that point. The figure of the geometric relationship is therefore as follows. The angle between the heading of the robot's body and the line of the sight is denoted by theta. Because of the robot is a rigid body and it moves around the circle, the instant center of rotation of the circle is shown as follows, and the radius is denoted by R. Recall that the steering angle defined the arc radius, and using bicycle modelization, we can find the steering angle delta as follows. But this is not sufficient. The pure pursuit control works in a manner similar to the proportional control to correct the cross-track error, using path curvature as the output of the controller. But it's important to note that the fixed value of LD leads to a curvature control that does not take into account the robot speed. This means that the selected steering angle would be the same regardless whether the robot is going with 10 meters per second or 100 meters per second, leading to a very different lateral acceleration, and the one tuned for low speeds would be dangerously aggressive at high speeds. To overcome this limitation, we add one more modification to our pure pursuit controller, and we can vary the look-ahead distance LD based on the speed of the robot by defining it to increase proportional to the robot's feed-forward speed. Relieving the adjustment into steering angle command equation, we arrive to the complete pure pursuit control The controller select the steering angle that will form an arc to the look ahead reference point and adjust it to be further away the faster the robot is traveling. Now we are ready to start building and specifying the PID parameters to regulate the velocity rotational angle. PID controller is a method for controlling an application to follow a particular value or path smoothly or through a comprehensive explanation of an application can be extremely complex. It provided a very elegant summary of math behind it and made it simple to apply the concept to many real-world problems. The goal of the PID controller is to reduce the amount of yaw error that occurs between the robot's hidden and the center line of the lane. The numerical model of PID control regulator given by the mixed form of the PID transfer function written in the force shown here. The following is a breakdown of how each of the PID terms gain and govern the response of the regulator and affect the steering angle of the robot. The proportional term, when it's used by itself to calculate the steering angle, it produces it that is proportional to the cross-track error. On the other hand, it fluctuates around the reference trajectory as a result. The robot's rate of overshoot around the reference trajectory is determined by the proportional coefficient Kp. The proportional component's overshoot is minimized by the derivative components by employing the rates of change of error. The robot's overshoot amplitude distance from the reference trajectory can be optimized using the derivative coefficient term Kt. And systematic bias cause errors in the steering angle over time, which could eventually, but not immediately, cause the robot to leave the track. This means it's corrected by the integral component. The integral component coefficient Ki, which is a significant impact on the performance as a whole, should be carefully optimized in a small step because of this component affects the error over time. The Kp, Ki, and Kd values could be manually adjusted through trial and error, but it would take a long time to get the robot to move around smoothly. Using an algorithm like Twiddle to automatically tune the parameters would be another option. And while this might be the best strategy, it requires some time and effort to implement the algorithm. We choose a tuning method that was easier than the previous two, and by comprehending the independencies of Kp, Ki, and Kd, we use Ziegler-Nichols method to select only two parameters to calculate Kp, Ki, and Kd terms. First is the integral and integral and derivative action are cancelled. The proportional action is increased until the output signal of the closed loop oscillates steadily. This gain is then noted Ku as a critical gain. We note Tu the period of the oscillation of signal. The parameter of the controller Kp, Ti, and Td are chosen according to the following table. So now our four-wheel robot model is complete and we are ready to visualize some results. We are taking into account a number of initial values to demonstrate the simulation system using a PID controller and feedforward constellation to examine the system fidelity. And these four systems, these four simulations of velocity demonstrate how system signal values dependent on whether the PID controller is used or not. If the PID controller is not used, the signal speeds up below the reference speed, while the signal with PID controller remains within a small error range of a reference speed. Also, the actual signal, system signal during flat uphill and downhill driving with a PID controller with and without feedforward controller with a reference speed at 10 meters per second. In this slide, steering angle shows that the motor loses control and the robot does not follow the reference in case when there are no controllers. The result, on the other hand, demonstrates significant role of our controller by demonstrating the system stability, and we can observe observed that the intended angle serves the reference for all cases when the controllers are present. The simulation also shows how PID controller with feed-forward consoles the effects of the disturbance and shows the real system signal and trajectory during the robot displacements. The system without using feed-forward also shows how these disturbances can affect the robot trajectory. In a conclusion, the mathematical unified model for the simplified ACC and LKA systems has been effectively delivered inside the study by the implementation of the track algorithm for the ego vehicle. The parameter for the PID and feed-forward controller that fulfill the system requirement are estimated, and the effects of disturbances is simulated. However, in order to quantify the result, all responses were compared because the model outperformed previous control strategies. More advanced control system will be used to test it in following research, and specifying the best road planification strategy for this model, and why not aiming to apply this model in with its simplicity in a real car and see how effective it can be. And these are some reference. And thank you so much.